We studied the damped oscillator in the actually physically interesting limit of the good oscillator. Now I will solve 3 problems for the damped oscillator. So examples. Example 1. Damped oscillator. So the example is this. Here we have a spring. There's a mass m. It is moving in a environment which applies a friction force, as we studied, proportional to velocity, but in the opposite direction. And initially, this is x-axis, and this is the 0. So the oscillator is at rest, and its equation is mx dot, that's equal to minus kx plus m beta x dot, but x is 0, x dot is 0, x double dot is 0. So at time t equals 0, a collision force, you apply to it an impulsive force. So this is, for example, time. We apply a force, a sharp force that extends from in times from 0 to 0 plus, namely in a very short. It's a kick. Okay. So let me integrate this equation from 0 to 0 plus dt. Let me apply that. The first is easy to integrate because this is acceleration is the derivative of the velocity. So it is m v at 0 plus minus v at 0. That's equal to, well, it is acting in such a short time that this has no chance to move. So minus k x dt from 0 to 0 plus, and this is an infinitesimal limit, so this doesn't contribute, plus and beta, this is dx dt, so it is x 0 plus minus x 0. Again, the object did not move. Here we have applied an impulsive force. And then plus dt fct from 0 to 0 plus. That means this is an impulse. Although it is applied for a very short time, it's a collision force, impact force, has a large magnitude, and it has a finite integral, and this we shall call j. So the total result is that originally our mass was at rest, so it is 0. This is 0. This is 0. The thing is that m, and this we shall call now v0, namely the velocity at the end of the application of the impulse. M v0 is equal to j, or v0 is j over m. That's the thing. So our oscillator's initial position is 0, and initial velocity is j over m. And let's find the solution. Although I've written the solution before, still it's a good exercise. Let's do it. X equals e to the minus beta t over 2 a cosine omega prime t plus b sine omega prime t. And x0 is 0. This is 1, this is 1, this is 0, so it is a that is 0, so a is knocked out. And the velocity b this is 0, a is 0, so it is multiplied by 0, and omega prime b. B is v0 over omega prime. So we are done. I am erasing this part. X of t is equal to e to the minus beta t over 2. And then b, which is v0 over omega prime, times sine omega prime t. Since v0 is impulse j over m, so we have j over m omega prime, e to the minus beta t over 2, sine omega prime t. So if we plot, for example, t, here's x. So at time equals 0, this is 0. At pi, so at every multiple of pi, 0, pi, 2 pi, 3 pi, etc. So it starts from 0 when it is 1. Omega prime t is pi over 2, for example. This is since beta, since td is much larger than t prime, or since beta is very much smaller than omega prime. Initially, it's just like 1. So pi over 2 it is here, x over jm omega prime, let's say. So this is getting damped slowly. Okay, so when you kick it, it begins oscillating, okay? And then oscillations get damped and damped and damped, and it loses energy with respect like this, E0 e to the minus beta t. And finally, of course, 4 times t very much larger than td, it comes to rest. That's the first problem. Our second example with the damped oscillator is that we have a mass spring system, and mass is moving in an environment which applies a friction proportional to its velocity, but in opposite direction, of course, because it's friction. But it is under the influence of a constant force, let's say F0. So let me write the equation again. M x dot. It's best to remember like this. This is mass times acceleration is equal to all the forces on the body. That's minus kx, that's the spring force, restoring force. Then minus m beta x dot, minus x dot. And, well, before time equals 0, in negative times, oscillator was at rest in its equilibrium position. It's 0 here. Okay? And at time t equals, after time t equals 0, we apply a constant force F0. You see, the first problem, which involved the impulsive force, and this one, which involves a constant force, these problems can be solved in the manner that we studied the damped oscillator. For general forces, of course, we have to do more, as we shall study in our forced oscillators. But this is forced oscillator, but forced in a very simple way, so that we can, as you can see, we can solve it very simply. So let me write it like this: mx dot plus kx plus m beta x dot is equal to f0. And let me bring f0 here, mx dot plus k x minus f0 over k plus m beta x dot is equal to 0. Now, of course, this is saying that change to a new variable. So let's change a new variable. It is tempting to change to new variable, x minus f0 over k. So y dot, the velocity of y, is the same thing as x, because f0 over k is constant, is like x dot. And y double dot is x double dot. And initial conditions, y0, the question is, where is y? So the 0 of y is at x equals f0 over k. So let's say f0 over k is here. So this is the 0 of y. 0, this is y, okay? So initially, talking in terms of the y coordinates, x0 was 0, so y0 is minus f0 over k. And y dot 0 which is x dot 0, which is 0. So the problem is this: m y double dot plus ky plus m beta y dot is equal to 0. You see, the force is completely eliminated, but we have a new coordinate y. And more importantly, we have a new equilibrium position. The equilibrium position has shifted from x equals 0 to f0 over k. And the y solution is easy. Let's simply copy from the... can we see that? I had written, so y is equal to e to the minus beta t over 2, y0. I'm just copying the result which we had found out at the beginning of the study of the theory of the weakly damped good oscillator. So I'm just copying from there. y0 cosine omega prime t plus v0 plus beta over 2 x0 y0 over omega prime sine omega prime t. And let us put the values. y0 is minus f0 over k. This is minus f0 over k. v0, namely the velocity of v0 y dot 0 is 0. And y0 is minus f0 over k. So it is equal to, y is equal to minus f0 over k e to the minus beta t over 2 cosine omega prime t plus beta over 2 omega prime sine omega prime t. Now we can switch back to the x because y is x minus f0 k. This is x minus f0 over k. Therefore, the solution x equals, taking f0 over k to here, f0 over k, 1 minus e to the minus beta t over 2 cosine omega prime t plus beta over 2 omega prime sine omega prime t. This is the solution for x. Bunch of factors. Let's see in a simple way whether we can understand this solution. I'm going to erase all the other equations. We don't need. I will only try to show x as a function of time. And to make the graph even simpler, I will again take the good oscillator limit, namely beta is smaller than, very much smaller than omega prime. So I neglected, this is 1, this is very much smaller than 1. So I neglected x equals f0 over k. 1 minus e to the minus beta t over 2 cosine omega prime t. So let us study the x as a function of time. So let me, here's the 0. And let me put here the time, omega prime t, this way. So, when time equals 0, this is 1, this is also 1, 1 minus 1 is 0. We are starting from x equals 0. Now, when cosine omega prime t, when omega prime t is pi, this is minus 1. Let us assume this is still like 1. 1 minus minus 1, that's 2. 2 f0 k. So it is here. So let me just drop a line here. This is 2 f0 over k. So when we apply a constant, so initially our oscillator was sitting still. At time t equals 0, we applied a constant force F0. It started to move. And then, well, it will not, it will almost touch, but not quite because of e to the minus beta t. So it's coming down. You can guess the rest. These intervals, of course, are the same. So this is, when does it go to maximum? At pi, okay? Pi is minus 1, 1 minus minus 1. It's at 2f0 k, so it is pi. And when it is 2 pi, it's 1. 1 minus 1 is like 0. So it is pi, 3 pi, 5 pi, 7 pi. Okay? So this is the behavior. We apply the constant force. It goes to the new equilibrium position, but it it passes that, does not really reach to f0 over k because this is not really 1 but a bit smaller than 1. Okay, so it makes a damped oscillation about the new equilibrium position. That's the physics of it. Okay, so damped oscillator with a constant force can be reduced to a damped oscillator with no force, but with a different equilibrium position. And if you start the initial conditions like that, at time equals 0, you apply the force F0. It goes to the equilibrium position, and then another example of this sort is this. Suppose there is a spring and an M, and you are holding this thing, and you suddenly, at time t equals 0, pull out the platform under the mass M, except that this M is moving in the environment which applies a friction force, and your constant force, of course, is mg. Okay, so it goes down, so it oscillates about the new equilibrium position. Let me just correct one thing about the sketch. Here you see, for example, it is coming here and here like that. Here the velocity has stopped and it has changed, so it should start the same way. So it's not coming out abruptly like that, but just like this. Okay. Velocity is picking up because the initial velocity is 0. Okay, so we make like that. All right. The last example with the damped oscillator, which, however, has a high Q value, is if we apply a rectangular pulse. Rectangular pulse. By pulse, I mean this. Our oscillator was sitting still. This is time t. At time t, we apply the force. This is F. At time 0, we apply a force F0. So this is F0. And at time capital T, so this is the shape of the force. The problem is, what's the response of our damped oscillator with a high Q? Remember, we found in the example 2 this as a solution. So we can make use of that solution, and let us find out how. Since the equation of motion is linear, we can make a linear superposition. So one force like this, F0, at time 0, remember this is the time axis. So this is the force F1. And at time t, we apply a force negative F0. So if you add them, this is, let's say, F2. But notice F1 is applied at time equals 0. F2 is applied at time t. So this is F1. So the total force is F1 and F2. But let us remember these shapes. So if you add them up, it cancels 4 times after capital T. And before time 0, there is no force. So if you just add them, you get the rectangular pulse. So we have solved it for a constant force. This is also a constant force. So we can use superposition. This was the solution for F0 applied time at time 0. So let me call it now x1. And for this thing, I will have a solution x2. x2 will be 0 up until time capital T, and then I know the solution. And I can write x2t as minus x1, minus because force is minus x1 t minus t. So, and I consider only the positive times, like here I am considering only the positive times of the argument from 0 on. Here, positive times means for t larger than t. So x of t, this full solution, x full t is x1t minus x1t minus t. I will not write x1t minus t because it's the same thing wherever you see. The only difference is that here we get the minus, it is that minus, and wherever you see t, you put t minus t. Okay? And then you can, one can plot the solution. There is an interesting limit. We may ask, what if f0 gets large, very large, and t goes to 0 plus, namely, instead of this pulse, this is 0, I get this mimicking the impulsive force. Does it have the same, do I get the same or similar result to our first example, which is the impulsive force result? So in this limit, let us compute. Namely, f0 is very large, t goes to small, and we are considering times larger than 0 plus. I am erasing these shapes because I need to calculate something. So let us look at the the full solution. X full t is equal to x1t minus x1 t minus t. Well, this is exact. To approximate, we do this. Expand this in the Taylor expansion. So it is x1 of t minus x1 of t minus dx1 dt times minus t. So these things cancel. So it is minus v1 of t times minus t, so it's plus times t. So all we need to calculate is v1t. v1 is dx1 dt, and so right here, it is minus v1 times minus t, it's equal to v1t. So let's compute v1, which is the derivative of x1. So v1 is equal to dx1 dt, and let me divide by f0 over k, which I can multiply later. So minus, so it is beta over 2 e to the minus beta over 2 t cosine omega prime t plus beta over 2 omega prime sine omega prime t minus e to the minus beta t over 2. Now the derivative is inside, minus omega prime sine omega prime t plus beta over 2 cosine omega prime t equals e to the minus beta t over 2. Let's collect the coefficients of cosine. Cosine times, here I have a beta over 2. Here I have a minus beta over 2. So that's basically 0. Plus the coefficients of sine. Here, beta square over 4 omega prime plus omega prime. Equals e to the minus beta t over 2. Now 1 over omega prime beta square over 4 plus omega prime square. I will now switch upstairs to make room. Let us remember that omega prime square is omega 0 square minus beta square over 4. So beta square over 4 plus omega prime square is simply omega 0 square. So we have V1 equals F0 over K times e to the minus beta t over 2 times 1 over omega prime times omega 0 square beta square over 4 plus omega 0 square minus beta square over 4. So beta square over 4 is cancelled, left me with omega 0 square times sine omega prime t times sine omega prime t. Okay, now I will erase this part. Let us also remember that this is m omega 0 square, so omega 0 squares cancelled. So x full equals f0 large t small limit. So this is f0 over m omega prime, and we had t, f0 t, times e to the minus beta t over 2. This t is, this is the pulse, 0 time t, 0 t, times sine omega prime t, which is equal to, if we call f0 t is j, the impulse provided by this pulse, sharp pulse. So it is j over m omega prime e to the minus beta t over 2 sine omega prime t, okay? Which is exactly the same result as the impulsive force result. Now, one technical point, I kept the full x in the derivation because beta squares cancelled and we get the exact result. Otherwise, if you just drop this term early enough, you still get basically the same under the proviso that omega prime is like omega 0. So if you make no distinction, you could have thrown this term out and you could have calculated faster. So this is the result of the pulse. In the limit, it's an impulsive pulse. But otherwise, this is our general result for an arbitrary rectangular pulse. This is the exact result. Okay, next time, we will force our damped good oscillator. Thank you.